What's going on, you guys? Mr. Allen here. We are about to graph this dope rational function here. We have f of x equals 1 over x squared. And since we're still in the really early stages of graphing rationals, we're going to table this thing out, and we're going to see what goes on a little bit different from our 1 over x that we've graphed to now a 1 over x squared. Woo! I think some dope things. And probably some similar things too. Let's see here. If I start with some numbers here, we got -4 plugged in. That's 16 when I square it. So we're going to have 1 over 16, and then I got 1 over, well, that'd be 9, 1 over 4, -1 squared is 1, so we're going to have just 1, 0. 0 squared is 0, right? So I'm going to have 1 over 0. That same thing happens there where that's going to be undefined right there. And then I'll just have, let's see, if I plug in 1, I get 1, 2, I'm going to get 1 over 4, and then I have 1 over 9 and 1 over 16. Okay, so one thing I'm noticing that's different from just 1 over x, these numbers are pretty large in the denominator there of that output, right? And also, everything's positive, right? Everything is positive. I wonder how that's going to look on the graph then. Let's get a few more numbers here. Let's do some fractions like we've done before. If I plugged in 1/2, 1/2 squared is 1/4, and then 1 divided by 1/4 is the same as 1 times 4 over 1. So I'm going to get an output of 4. And then 1/3, same kind of idea here, but I'm going to end up getting 1 over 9. So 1 divided by 1 over 9, flip it. We get 1 times 9 is 9. And then 1/4, I would get 16. So it kind of works its way, very similar to what you see going on in there. And if I plugged in a negative, right, squaring it's going to make it positive. So I'm going to get the same outputs, whether I plug in positive or negative 1/2. Whew. Let's take a breather. Okay, I'm good. I'm ready to rock. I'm too excited about it. All right. If I plug in -4, I got 1 over 16. I'm really, really close to that x-axis. -3, 1/9. I don't even know if I can make it look right. Then I got 1/4, and then I got 1. Boom. And then the same happens over here, right? It's like mirrored image. Okay, that's kind of cool and interesting and wonderful. Okay, there we go. Right, we're getting really, really close. 1/16. That's super close. Man, if I plugged in like 1 over, or plugged in 10, I'm going to get 1 over 100. It's going to be really close. Well, I plugged in, something even bigger. It's going to be even closer. You're not even able to see it out there, but it never touches, bro. All right. So let's see here. When I did 1/2, we got 4, and then I'm off the graph after that. So we're just going to stop there, but we know it's going to keep going up there, right? So if I connect my dots, the most fun part of graphing, right? Whee! Arrows, and then, all right, woo, wee. Okay. There we go. All right. Now, next thing, what's at 0, we said at 0, we couldn't plug that in, right? We couldn't plug in 0 for x. That's a no-no zone. That is our vertical asymptote, all right? That's a vertical asymptote right there. That guy, you cannot cross or touch a vertical asymptote, all right? Just get real close to it, right? Be like, hey, asymptote, what's up? Don't touch it though, right? Not good news. Okay, so there we go with that. And then what about, what's going on here, man? What's going on here? Can I ever get a negative output right now? Well, my denominator is always going to be positive because it's being squared. No matter what I plug in, it's going to be positive. And my numerator is always 1 here for this one. So sounds to me like we have ourselves a horizontal asymptote at y equals 0. So this is y equals 0. This guy is x equals 0 for my vertical asymptote. All right. Dope. Let's fill some of these things out, shall we? Let's do it. I'm going to switch colors, right? I'm a little tired of the blue. I'm going to go with pink. All right. So end behavior. We've dealt with end behavior in polynomials. Now, that's just when it's going to the left and to the right. So as x approaches -infinity is all the way over here, right? My graph is getting closer and closer to 0. So f of x is approaching 0. Not equal to, my goodness, Mr. Allen. Approaching 0. That's an arrow there. That's a fat arrow. All right. Then as x approaches positive infinity over here, that's going to be positive infinity, right? Ugh. There we go. F of x is once again, it's just getting closer to the y-axis, right? To the x-axis, closer to y equals 0. So my output, or my graph is going to be approaching 0. There we go. All right. So as we go to the left, it approaches 0. As we go to the right, it approaches 0. But what's it doing around that vertical asymptote? We have this x equals 0 vertical asymptote. Both sides are going up, right? So as I approach, or as x approaches, let's see here, 0 from my left-hand side, right? That means from the left, I'm going to be going up on this side. So f of x approaches infinity. And as x approaches 0 from the right-hand side. So on this part of the graph, right, I'm coming from the right. Woo! I know I'm moving left, but I'm coming from the right side, or on the right side of that asymptote. Then f of x also approaches positive infinity for that one. So one last thing, man. One last thing I want to do will be our domain and our range. So what do we have here? For domain, I just cannot equal 0, right? X does not equal 0. Okay, that's the most clear-cut, in my opinion, way of doing it. You may have a teacher that wants you to do a little bit more fancy notation, get some brackets, get some all real numbers, except x cannot equal 0. Dude, this is fine. Calm down, people. Calm down, all right? You know, if you want to debate with me, feel free. Pop it in the comments. I think that's Gucci. It gets the point across. Range here. Now, I feel that probably the best way of writing this one out is, well, I can't go below this, right? I just said that y is always greater than 0. Can't be equal to 0. It's got to be above 0. So the inequality, I think, is the most efficient method there. You can also use things like interval notation. So let me do a little interval notation here for domain. So my domain interval notation would be from negative infinity to 0, right? And then union 0 to positive infinity. And my range would be from 0, not including 0, to positive infinity. So really the range one, those two notations are pretty, pretty similar as far as like the amount of work that's involved. But I feel like interval notation, when you're dealing with asymptotes, it gets kind of messy, man. It's just like overwhelming. Like that seems to me like the most easy, clear cut. I know it doesn't equal 0. Here I'm like, I got to read all these infinities, man. You know what I'm saying? It's kind of lame. All right. Enough of my opinions here. Enough of my opinions. I think that's pretty dope. That's awesome. So when you have something that's squared in your denominator, a factor, or just an x, or when you get going more like x plus 2, quantity squared, you're going to notice that it approaches that asymptote on the same on both sides of it. And that is something that is going to occur. So start looking for some of those patterns. You can start knowing if you're graphing things correctly when they get more complicated. We're going to have stuff in here, man. You're going to have to factor here soon in these bad boys. You have to cancel things, simplify. It's going to be dope. All right, see ya.